I didn't want to, be really fun. It's really difficult.
Okay, the talks this week are going to finish up the atomic physics, and particularly the parts we need to continue doing the molecular analysis. Right now, the electrons are providing spin in various arrangements described by one kind of tableau, and then there's a conjugate tableau to describe the orbital part. And that's that will happen in the molecules, where the nuclear spins will take the place of the electrons. And then the rotation will take the place of what we call orbital in this atomic analysis we're doing here. Now this analysis by tableau is really helpful, since it allows you to do some pretty complicated problems that most people would require a computer fairly easily on paper, or on using something like Mathematica, which lets you organize the matrices very quickly. Then it becomes really very simple. Okay, so I do want to go over in detail the business that involves this so-called jawbone formulas. This is a jokey name that I came up with when we first noticed this was possible. And so I want to go through each of the matrix components in this particular example we're doing here, which is the doublet of a P3 atomic configuration. That would be nitrogen most commonly. And I want at that point to take a look at what the angular momentum operators look like, but also today I would like to show how do we do electronic repulsion. That's really quite a daunting problem, to be able to work out the electrostatic interaction. This is not something we worry about, at least at first, in any of the molecular stuff we're doing, because they're in a nice framework and nuclei are more or less behaving themselves, but electrons don't behave themselves very well. They're all over the place. And so how do you get the, well, it basically uses the multiple addition theorem, which I'm going to rename, to do that. But how do you do that with the tableau arrays? That's the real thing I want to cover today, from a number of different viewpoints. So at the end of the class here, we'll go ahead and look again at the nitrogen configurations and talk a little bit about the physics. The very end of the room is what I dug up from the internet as far as nitrogen goes, and in particular as far as Hund's rules, which is something that is really quite counterintuitive if you look at all of the rules, all two of the rules in particular. So let's go ahead and get started here. We're using right now the references pretty much from the anything that has Young Tableau written on it, but the actual original papers. I'll give those references later on. So here is a matrix I want to analyze, make sure that we see how each of the components are gotten, starting with the upper left-hand corner here. Now, what we have here, just to refresh your memory, is tableaus. In this case, it's a tableau that consists of two boxes in the first row, and then one box in the second row, having an overhang of 1. That means that it's going to support, in the conjugate tableau, a spin a half, which is what we call a doublet in atomic spectroscopic jargon. And the 1, 2, and 3 that we're talking about here occur as quick ways, I think, the most easy way to deal with the U3 physics that we're dealing with here, which is the P shell, but for just a single L = 1 particle, our index 1, 2, and 3 that appears in all those numbers in parentheses or in the kets that belong to tableaus, all of those numbers correspond to 1, 0, and -1 respectively. So I will make sure that is very clear, because as we count up on our index 1, 2, 3, we're counting down in the actual angular momentum that they represent. So just if that wasn't clear before, I hope it is now. So what is happening here is that each of these numbers here that are in parentheses refer to an operator such as the very first one here is 1, 1. That's the number operator, because the number stays the same. Basically, destroy a 1, create a 1. That's the process of counting. So it's looking at this tableau and just saying how many 1s are in that tableau. Well, there are 2 1s in it. So it's a diagonal matrix element sitting on the diagonal of this 2-1 tableau representation that we're going to go through in detail. And I want to make sure that this particular part of this formula is, well, it's a very easy one, but that's the start. Okay, so we're looking here at counting the number of 2's in the next part here. This one counting the 2's, only 1 there. So we have 2 and 1 showing up there as the matrix element in question. Okay. Now later on, you see, we want to turn this whole matrix into one of the irreducible tensors, say dipole, quadrupole, 5 components, dipole, 3 components, and then of course as a scalar, that makes it a total of 9. But when we do that, we'll have to look up the number in the tensor, the irreducible tensor matrix for each of these guys that are in the parentheses, because they have a coefficient that makes whatever tensor you want to make. So the procedure of converting this to a physically useful thing is the key second half of what we need to do. But right now I just want to get the mathematics of getting the irreducible representation numbers correctly based on that crazy stuff there. Okay? So, first part, numbers, that's not so difficult at all. But the next parts are all, we're going to go through everything that's in green here. Okay, all of the stuff in this block here, this block here, and this block here. They're all corresponding to a single jump operator. That is an E that destroys an I and creates an I minus 1. Okay, so remember using the 1, 2, 3 indexing. So that's bringing it down. This is actually raising the angular momentum. Okay, lowering our index count. So 1, 2 of 1, 2, 2. Okay, that's destroy a 2, create a 1. It just looking at the tableaus, yeah, that's right. But the idea of doing that is based upon a particular rule here. Now this is a rule that shows the tableau, and we're starting with I and changing it to I minus 1. And the ones that have a little black around them indicate the box that actually is getting changed by this particular one jump down operator. And this is a particular case where the tableau has in the first column both I minus 1 and I. If that's the case, there's nothing fancy going on. This just becomes a 1. So each of these satisfy a fairly simple rule there. And this one right here, in this case I've got a 3 is part of this thing, and if that's the I, then I minus 1 is 2 for this one jump down. And so this 3 is becoming that 2 right there. There aren't any other 3's in there at this particular juncture. So this is a pretty obvious thing. But it has to be, you have to be aware that if none of the numbers besides I and I minus 1 are anywhere in the tableau, that's just shown as a blank. So the different cases correspond to what you have in the tableau that isn't I or I minus 1. All the white regions are other numbers than those two. But if those two show up elsewhere, then you have the different cases that we are going to be going through here. But again, this is a very simple one that just gives what you would expect from an elementary operator, but you can't expect it always in a complicated tableau. And here's one that actually gives you a number. In this case, we're having a battle between I and I minus 1 in the same tableau, and we're actually going to be changing one of those, namely the 3, and making it into a 2. And so we're starting out with an I minus 1 operator on the two numbers that are separated by a city block distance. And you have to think of a tableau as a kind of funny city, say Manhattan, New York, only a very reduced version of that, where it only has one block of streets this way and then another block of streets this way, and you're asking, how many streets do I have to cross minimum to get from this box to that box? And that's really what a hook length is. This is the hook length distance. So how many streets do I have to cross? I have to cross one street to get to the 1 and then another street to get to the 2. So this is a hook length distance of 2. And actually this is wrong here, it's I equals 3 is what we're dealing with in this particular case here, where we're destroying a 3 and creating a 2. Okay, so in that case I take the hook length d minus 1 over d. And that gives me the square root of 1/2. Okay, that's it. So this, what we're going to do is just go through each of these finding cases so we cross each of the different cases at least once before we finish this matrix here. Okay. So stopping at any point when you see something that is weird. And remind me to make a correction on that particular little I equals 3. This case here, I think we're talking about I and I minus 1 again. I think I did the same thing on that one. Not to worry though, because in this case, what we're getting here is a d plus 1, a distance plus 1. Okay, distance is still 2, but this one comes out to be a square root of 3 over 2 for the one here. So the important part of all of this is when you make a matrix like this, you've got to leave an indication of which of the operators did the job. And this is the 2, 3 operator. Okay? So I think you see the reason or the method of this madness. Okay, that's the main purpose of this first part of this lecture today, is get some of that out of the way. Here's another example right here. Okay, this is again one. Now in this particular case, this is kind of a funny one. We're destroying a 1 to create, destroying a 2 to create a 1. Okay, so we're talking about I equal 2. That is correct. But now the distance between the two is just 1. Okay, the 1 is located just across the street, one crossing from the 2. So the d equal 1 is put here, and that's square root of 2. And this one is also indicated right here. This is the largest matrix element besides having a 1. Actually, the 1, this is larger than 1. This is the largest that this formula ever gives. Okay, and for this particular tableau we have here. Okay, you're really close, and you get a situation or you get the square root of 2.
So it's from that formula that you're making that.
Yeah.
Okay.
In each case here, I'm put a little blue around where I got it. Okay, and of course this is just a special case that was in that particular description. Okay, and then as we work our way down into the lower portions of this matrix, another one comes up. This time it's involving 2 and 2, 3, 2, 2, 3.
Those
Square
are
root
harder?
of 2. Yeah.
What does, for example, like when you have like D2, 3, you're destroying
Here.
the next one next to that?
Oh, this one.
Oh, yeah, that one. Yeah, that one.
I can
So
go
you
back
create-
easily to that one. There we go.
You destroy D3 and create D2, right?
That's right.
But how does that, like, why, how can I tell, like, to use, like, the hook length, like, 2 plus 1 divided by D?
Well,
Why is not, like, 2, 1, 2,
when you apply 2, 3 to 1, 2, 3,
uh-huh,
okay, here's 1, 2, 3, okay? Here's 1, 3, 2, okay, when it gets a destroy a 3 created 2, it gets a very different number, right? This is the one that we're doing right now. Okay? So I've got 1 and 2, that's I and I minus 1. And we're looking at this guy right here, and what's happened is that this box here is actually slid up next to this one. So that's the thing, maybe the separate case should be shown, but it's still giving the same number. I'm still going to use that distance, but now the distance is 1. The D, I'm sorry, is that right? Let's see, the distance between the two numbers that I'm working on right now, 2 and 3, is 2, okay, for this one. So I'm using a 2 in that formula right there. 2 minus 1 over 2. 1/2. Square root of 1/2. Does that make sense? Yeah. Now, we're going to go through these maybe a little too quickly. This is something you really ought to study on your own and do it for later on, bigger tableau system. But let me get the basic ideas, finish answering your question before we go on. Do you?
yeah. I mean, I think it's just a matter of knowing the length of the young tableau using the length formula.
The D that's shown here, okay, well, here, because that's the one we're using, right? The D here is between I and I minus 1, right? In this case, we're starting off with this guy as an I, and I keep making the 2, 3, so I'm going to have to go back and change that. It's not critical, but the D's the critical one, and we're going across the street. That's 2 for D, okay? And we've got to use this guy, not this guy, for this one. So
Why?
we get D minus 1, 2 minus 1, and then just plain D, which is 2. For this particular case, you see there's really 4 cases that give you a number besides 1. And that's what makes this a little crazy.
Okay.
Is that,
Yeah.
So I've got, vignettes for every one of the ones in the green, and then we've got to also do these, but they come out very easily. You think they would be hard, but they're not, as we'll see. Okay, so these are the crucial ones. The ones in the green are just off the diagonal, and they're making a change of 1, not 2. You think the 2s would be harder, but it's not, because you've already done 1, you just do it twice. That's what will happen. Okay? All right. I think the end of this one is right here. We're looking at it already, but there is another one here to go through. We're now down in the lower portion there, doing a 2 destroyed and created a 1. Once again, this is a D plus 1. But D is only 1, so we get a square root of 2 again. There's another one that's in that box there. This thing, it's a 3 destroyed 2 again. This one gives another square root of 1/2, not too different from that one. And there's another 3, 2. Okay, this one gives 3 over 2. Okay, square root of 1.5 instead of the square root of 2. So these are some of the larger numbers in the tableau. And then there's that little guy right there. I skipped the 1, 2 there. You can look at that yourself. Okay, so now we got to get the guys in the red region here. And let's start off with that one. Okay. Well, here's destroy a 3, create a 1. That's a jump of 2. So I've got to convert this guy to operators that only jump by 1, which I've already worked out, you see. So all I have to do is keep my eyes open where those guys are acting on a particular tableau that we're interested in, and I will just apply them. But I have to apply this one and this one. That's the commutator. So this is a little trick of turning the elementary operators. This is their commutation relation, which they satisfy. They satisfy a product relation that's not too different from that. Basically, the product relation, if you were to be able to use it, you can't in a Lie algebra. But you would put these two together and get an E1, 3, and that'd be it. But here we have to write them as commutators. So that's the one fly in the ointment of Lie algebra that doesn't exist in group algebra. Okay, we talk about elementary operators there. It's just a product, and it's like the ket bras hitting other ket bras, right? No commutation at all. But here you definitely need the commutation. So once you have that, then pick your basis that you want to hit. Okay, now we know how to do it. Okay, we have to find out what 2, 3 does to 1, 2, 3. Okay, well, it turns out we already have worked out most of these. We already have these numbers. I don't need to go to that table anymore. I already did this one, right? So I'm going to get my square root of 1/2 right away. Okay, and my 2, 3 on 1, 2, 3, that's what we're working on. 1, 2, 3 is getting hit by 1, 3 and by 2, 3. We've already done that, this one at least, and we've opened it up so that next step will be a 1, 2 on whatever this gives. So that's not so bad. Same thing here. Okay, I got a 1, 2 operating on 1, 2, 3. And I know what the answer to that is. It's square root of 2. And this one is square root of 2 in the denominator. So we're almost done here. It's just we have to do the E1, 2 on that thing. But we have that as well. Here's the one that gives that for the 2, 3, but it has a minus sign now because of the commutation. And then this one right here, we already know what 1, 2 does to 1, 2, 2. So those two numbers go together now. It's the square root of 1/2 minus the square root of 2. So we're getting a negative number out of this one. Okay. Square root of 1/2 minus the square root of 2 is minus 1 over the square root of 2. And that's what we have. So there's the answer. Okay. Without looking at these rules. The rules of art, this is all for one jump. And we're just doing 1 jumps in succession now. Okay? That's pretty cool. But that's the way you can do this by hand, right? Finally, you program a computer and do it very quickly and out of sight. But here's, maybe your computer program had a mistake in, you're going to have to check it. I mean, it's at some point. That's what always happens.
Dr. Harter?
Yeah.
How come he 1, 2 just destroys 1, 2? Like, okay, so he just destroys the 1, 2, there's 1, 2, 2, like it seems to me like he will destroy like the 2 2s, right?
Good question. Another unwritten rule here is you cannot have two numbers the same in any column. And we've got a second column here, and so if I were to destroy this particular, destroy this particular 2 here and create a 1, 0 automatically, because this is anti-symmetric.
Okay, then the complete expression you should have written, there is like the 1, 1,
tableau.
Because it does two things to that thing.
Yeah.
It does, and then it does the,
And one of them dies.
yeah.
So you only get one thing.
So it
Yeah.
just, and then you have like the 1, 1, 2, like 1, 1, 2.
Mm-hmm.
But you should have also 1, 1, 2, like 1 in the vertical. And then for the 2, 3, well, there is only one for the 2, 3.
Yeah.
You just get
Spot
1, 1, 2.
I dare not destroy that one and make it a 1. But I'm perfectly good at doing that.
Okay.
And we could go back to the rules over here about that, but that has already been done, okay? This
built in.
1, 2, to make that has already been done.
Yeah. The difficult part is that. Like that,
This part,
yes.
yeah. But after you get a few of them done, you've accomplished all of the changes that you can make by one jump. They're, you know, waiting for you in the green area here to help you in the red area. Now this is U3. If you're U4, you've got another set waiting over here, and then if it's U5, which is a D shell, you've got yet another area. But the same thing's true. Each area takes care of its job, and then the next commutation is just making use of two things that you already have in the lower region that you're there, than you are. So here's another example here. This particular one is kind of interesting. Destroy a 2 and create a 1? No way. So that commutation term with a minus sign is out of here, 0. But I still have something here that I can do. I can destroy a 2 and create a 1 on that one. Same argument. I've already done that. So I get a square root of 3/2. That's that thing right there. To add to this one, okay? So the 1 then multiplies that to give square root of 3/2, which is the answer for this one. Okay? So we've done a couple of double jumps now, fairly easily. And the others, there's no reason for the other ones to be that. I don't think there's anything tricky that pops up now. This is kind of an interesting one. It's out there, it's sitting there on the anti-diagonal, okay, with a minus sign and nothing below it, nothing to the side, either side of it. That's kind of a neat thing. Again, destroy 3 and create a 2. There's only one 3, and it's nothing going to let me get anything but 0 out of that one. So again, it's just one term which we can look up. And then together, those two make the answer -1. Okay, -1 over the square root of 2 times the square root of 2. All right. So far, so good. Okay. We'll I'll leave the rest as study material. Now, this is for later on. Just want to remind you that the basic matrices that sit in the tensor table, that's the table that gives you the V's, the little V's for vector, but they're all of them are in some sense vectors. The V just is notation that's pretty common for tensor operators. The angular momentum LZ is in fact the square root of 2 times one of those unit tensors that we keep in the tables. And I meant to throw the table up here. Look, we've got plenty of examples of it later on, so that's no loss. But just to get a feeling for where the square roots of 2 go and where they don't go, notice that in order to actually get a L plus raising operator, the kind that I use in angular momentum, ordinary freshman physics, angular momentum raising and lowering, has a square root of 2 on it. These guys, these U3 operators, they exist with a 1 over square root of 2 when they're in the table. So each of these things right here, this one in particular, is the square root of 2, which is multiplying the one in the table, and the one in the table had a 1 over square root of 2 times that. So the relationship between the angular momentum space and this U3 space is not, it has some of the similarities of the relation between spinors and the vectors, the L vectors that we're talking about. So there's Lx and Ly, the three-dimensional spinners, if you like, sitting there in their raw form. This one has a 1 over square root of 2 in front of it. Okay, so lots of chances to make errors of factors of 2 and 1/2 as you make the change between our elementary operators and the old-fashioned angular momentum L orbit operators. Okay, here's where it gets squirrely. We need to take this matrix that we've created here and multiply it by itself, that is, square it, in order to make the multipole electrostatic repulsion. Call it a tensor if you want. It's a scalar, obviously. It has to be invariant to all of the rotations that we would normally consider in a free space around a nucleus of an atom. So I first want to go over again. We've already looked at these once, but it doesn't hurt to look again at the dipole, quadrupole, octupole, hexadecapole, etc. And the Legendre functions, where they come from, just to remind you of the source of that very important mathematics. This is such a beautiful a piece of mathematics. Now, what we didn't do in this class is do the complex analog of this, and that's in that chapter 10 of the introductory unit to classical mechanics with Bay. So don't forget that goes through very similar arguments here. It just doesn't mention Legendre polynomials. It doesn't have to, because complex variables are so powerful. So the very first step here is the 0th order Legendre polynomial. That is 1. P0 of a cosine of theta is not a function of anything. It's just 1. Q over R. So that's the Coulomb field of a single, well, it's going to be a single electron, but if we were doing studies of the Schrodinger equation for each of these one particle, this would be the potential. That would be the only potential we would look at. So now I want to remind you that we're going to go over this fairly sketchily. So this Unit 8, the study of wave functions, begins on page 24 of that unit. That's in PDF pages, but just click on that and you go right to it. And then a little bit later, 33 is where the real meat of this discussion begins. So this is a link that you may enjoy. In any case, after I get a particular level of multipolarity, I then take a single derivative. In this case, I'm doing it with respect to the z-axis. This is not a complex variable z. This is the real z coordinate here. And the effect on r to the -1 is going to be, well, we get here the result nr n-2 if we have already n to the r to the n-1, and then times the partial derivative with respect to c of the actual r vector. Okay, so the result for this is a dipole. Okay, so now we have the first Legendre function, which is just cosine. P1 of variable x, or whatever you want to call it, is x itself. So these are the first two that get us started, and then from there on we start getting the really complicated functions. But the very first one, the dipole, as I recall, you remember that cosine, plotting something as a cosine in radius. The radius changes as you change the angle and it comes back again. That makes a perfect sphere. Remember the Thales geometry of this crazy thing. But from now on, they're going to be elongated. The next thing here is the quadrupole, and it has P2 cosine over now a higher power of R, and then so forth. There's the octupole, okay, that's P3. So we're talking about a thing that has 2 to the 3, that's 8 collections of charges that it has. There's 3 things, and 1 is 4, and there's another 4, that makes 8. So the Pascal's triangle of charges is lying above these things. And the general case is that derivative right there. The Lth derivative gives you a 2 to the L pole. I should have used the letter K there actually, but we'll be doing that enough later on. So here we are all the way up to 2 to the 5, the 32 pole arrangement. Okay, and there are the Legendre functions that make it. So these are the functions that we're actually going to be using to make the electrostatic repulsion Hamiltonian for the electronic, the 2 or 3 or 4 or 5 electrons that we'll have flying around the various atoms that live in the P universe. Okay, so we got a bunch of multipoles, but they're all on a single axis. All of those things are lined up on an axis, making some kind of wave functions that's cylindrically symmetric around that z-axis. So we've got to move off of the z-axis. That means we have to do some group multiplication. I rename multiple addition theorem officially now the group multiplication theorem. You'll see why as we actually move it off the axis. Okay, so while we're at this, I'm going to go ahead and bring this guy up to where we are, and this one seems to have some CPU problems. There's a little past where we are, but that's the basic idea, is that I want to go off the z-axis to some position alpha of beta. I don't want to twist it, so I'm not going to change the gamma angle of the Euler angles. I'm just going to do the azimuth and the polar beta rhymes with theta angle, and not touch that thing that we called the overall phase when we were doing our 2-level stuff. Okay, so the off z-axis Legendre polynomial wave has just had a Euler rotation, 2/3 of it anyway, applied to it to give us a multipole that's pointing in some direction. Okay, and that means it has a wave function described by the rotation matrix alpha beta 0. Okay, now that particular irreducible representation is equal to a spherical harmonic YLM star with this little normalization factor and the polar coordinates being alpha and beta, our azimuth and our beta rhymes with theta angle. So that little sum there is the beginning of what we need. So at a particular position, phi theta, that is, let's consider a bra of a position that has angles phi and theta, completely arbitrary, generally different from alpha and beta, but possibly the same if they do the repulsion between the one electron and the other one, which is what we're actually doing now, is thinking about the possibility that another electron might be here with those coordinates. That's the whole idea of this exercise, is to accomplish that. In any case, that's what we're dealing with right here. Now this function here is another spherical harmonic. This is the spherical harmonic Lm, forget the other index, other quantum number, the body quantum. This thing doesn't have a body, it's just a line, and that's the YLM and the YLM star we've already got from this operation, R alpha beta here. That is that, but that's YL star there. Exactly. Okay, so this is a wonderful exercise in spherical trigonometry. If you go through where all the angles are with respect to each other, I would have you take a look at that And that begins on page 33 of the unit, and there's the link to it, with this picture blown up so that you can see. So we have the regular z-axis here, and then we've got two other axes here. One at phi theta, that's the second electron, and the one at alpha beta is the first electron. That's what's going on here, as we have created now a Hamiltonian for that really complicated system of two electrons. Okay? All right. Problem is, we've got three, right? What are we going to do? Well, stay tuned. That's where the stuff we've already done comes in. All of the U3 stuff is waiting to take advantage of this Hamiltonian. Okay, so that's the basic idea here, representing this group product, which will give us some other set of angles. Okay, this is a product that gives me a particular angle, phi and theta, uppercase. And again, we're not messing with the zero here, and these are all zeros, so we're not messing with a phi either. It has, whatever this is, has a spherical symmetry. That's this thing. Okay, and it's just a Legendre polynomial. Okay, that's really cool. Okay, so this is the multiple addition theorem. It was gotten by group multiplication. There it is. The Legendre polynomial, that's this thing, but floating out at some angle, big theta, with respect to the z-axis, which is also out there floating around somewhere. Okay, that is this. A sum over, well, L tensors, two of them. One of them starred and the other one not. And they're functions of their respective angles. Polar angles. First, phi and theta, we're used to that notation. That's this guy. But we started with this one, alpha beta. Okay. All right. Now this is stuff that's in Jackson, but Jackson is notoriously obtuse, I think. Doesn't explain what's going on very well in that. At least I had a horrible time with it. So I'm trying to rectify that. Okay? All right. Now, here's where we actually make the electrostatic interaction. Okay? This guy, 1 over r, that's what we did, but we're thinking now of a vector that's a difference. It involves this expansion of the Legendre expansion, but that Legendre expansion has this expression in terms of the actual polar angles of the two objects that are here. There's an object that has a radius r alpha, that'll be the alpha electron, and there's a beta electron. Okay, the catch is that you can't really write just one function for this. You've got to put some indication that makes this one down here be larger than this one. So at some point, these electrons are going around, say the center board is the nucleus, they're going around, and this one's closer, that one's farther away, so this one's got to be the beta electron, this one's got to be the alpha. And then they fly around a little bit. Suddenly this one has got to be the beta electron, and this one the alpha. So that little trick to make this sum here converge is very much a part of this thing. So R alpha will always be closer than R beta to the nucleus. And this is the shorthand tensor form for this interaction. So it's going to rewrite this thing this way, where these are our multiple functions. I usually use a big X to indicate them, but they're the spherical harmonics with this extra 4 pi over tensor dimension is what that K is going to be for us. And then here is the actual K that they have. So I'm replacing K, the L here, with the rank of the tensor products, quadratic tensor, that is going to be our Hamiltonian for electronic repulsion. And that, of course, opens a fairly large can of worms. including all of the integrals that you will have to do if you really want to figure out what the coefficients of this angular part are. So these are called Slater intervals, after a very brave man who was first to figure out what integrals you had to take in order to actually get the coefficients of the beautiful group theory that we're going to be doing here. Now, that brings up another topic. If, in fact, this were two electrons orbiting around a single nucleus without a core of other electrons, that is, a very weird hydrogen that had more than one electron, then I could use hydrogen radial functions to calculate this a function. I could also make use of the O4 symmetry that the radial part of the Coulomb field has to do group theory and get these quantities. To my mind, as far as I can see in the literature, this hasn't happened yet, but it should. I think there might be something neat in that. But quite apart from that, it turns out that you can use hydrogen radial functions, just shift the R a little bit. It's called the quantum defect. You put that in and get those integrals and do a pretty good job of getting all the numbers that you need to do this atomic physics. We're not going there. And you all say, oh, I'm glad of that, because that is a long journey. You can do a whole course on just getting those integrals for even this problem we're doing with 3 electrons. And there are all sorts of parity things going on here that allow you to cut down on some of the extra phases and things that you have. But this is what we're dealing with, and this is what we have to handle. So we have to use these things to give us, through our tensor matrices, the actual Hamiltonian for this problem we're doing here, up to a factor. So we'll be getting answers here that are differences in energy levels. We will not be getting the absolute values of the energy levels unless we work out those guys, the Slater intervals. Okay. All right, so that's something we don't have to do in molecular physics for the rotating molecule, but we've got lots of other constants that we can evaluate, first principles in that problem. So this is how it works. This is the preceding page moved up, and with this 2-particle, the elementary operators expressions, and it involves 2 of them. That's what we're after. And then these little numbers here, the K and then 2 indices, those 2 little pockets, those coefficients, those are the coefficients of our tensor matrices. They are Clebsch-Gordon coefficients. We'll go over that a little bit, just to clarify it a bit. But remember now, when I talk about the indices, 1, 2, 3, and so forth, what we're going to be doing is we're meaning both the total angular momentum and the z component. Now for today, we're only interested in this. We're going to have an L equal 1 everywhere. It's just going to have a variable of m here that goes from 1, 0, and minus 1, which we call 1, 2, and 3. Okay, so this is just getting ready for what would be the rest of an atomic physics course in which we tackle, well, D shell, F shell, but mixtures of D, F, and P. Those are all ready to be used with this particular bunch of formalism. Now, the other thing that happens is the radial integrals fold up into a combination that involves all of the orbital angular momentum, whatever rank the tensor is that you want to take here, and we'll have only one rank possible in the P shell, because the P wave function can't feel a K greater than or really less than 2. 2 is the only k that this particular model is going to need. So we really have a pretty easy for the p-shell. Anyway, the n particle elementary operators, here are the single particle elementary operators. We're going to be replacing those with something that sums over 3 particles today, because we're in the P3 configuration, and we're going to be using these elementary operators to satisfy those very simple rules, but the commutation rules are what we look at when we look at the grown-up elementary operators. So this is an actual expression here using the elementary operators that we just worked matrix elements out. So we're going to have a big matrix that we just worked out here, a component of it for that particular set of indices, and then we're going to have another one for some other set of components. That's going to be the number we'll actually work on. This one just turns out to be a constant. It's called the, in our cases, it's called the self-energy. So it's something to add on to some numbers that we don't already actually know. All of these numbers are sitting here multiplying it, so they're going to be undetermined constants. So is this. So all of our meat is going to come out of this. Okay, just to see how dreadfully I've simplified what we're doing today. So here are the tensor operators big V, as opposed to little v for single particle. These are for any number of particles in any collection of 4 different angular momenta at a time. That's a pretty big order to handle. So we've got some thinking to do here. Okay, so let's finally look again at those tensor tables. And these are arrays of these things that I call rank K, and then 2 indices indicating the Z component of the atomic orbital angular momentum. And then the VKQ has got to be written in terms of the elementary operators. So relating those two, I mean, this is going to do it a couple of different ways that I thought you should see before we go on, and really take another tack that does this summing of the elementary operators. Okay, so this reaction, interaction, Hamiltonian, has been cheapened to the point where we're basically just looking at some constant here. We have a single orbit, L equal 1. We're going to have a single rank, K equal 2, and we're going to be off to the races on that for the nitrogen atom spectroscopy. So we're going to have to take a dot product if we want to, follow this all through. So it's worthwhile looking at what that looks like, but it also means looking once again at what the individual V's look like. And as I say, we've already calculated a very big matrix built out of numbers from this table right here. So these tensor tables, of which we've already shown for not just the P shell, which is this one, but also the D shell and the F shell and the G shell. And I'm going to show you some more at the very end today where we mix a couple of those together. Those are what this is. Now the way we usually display these is in this compact or compressed form where I just slide all of these matrices together, because you see none of these matrices uses the real estate that of any of the others. So this one sits down in the corner, but then none of these have anything down in that corner. And the same thing's true of every one of the dots that are shown here. It's very easy to simply put these all on top of each other. Okay? And I think I've explained a little bit about this, but I'm going to go ahead and explain it again with some graphics, just so you know what we're talking about. And the important part of this is that the normalization factors, or whatever you want to call these coefficients, and those are numbers we have to look up to put on top of the matrix that we just created at the beginning of this class, I have to make sure that I multiply that by 1. I don't have to do anything with that one, but I have to put a 1 over the square root of 2 on both that number and that number. And then this one demands that a 1 over the square root of 6 go on that number and that number. So each normalizing factor, usually a 1 over square root of an integer, sits just below each 45-degree line, demanding to be added to each of the ones above it. Okay, so that's true over here as well, but you see there's a 1 over the square roots of 2 that need to go for each of those numbers. So it's just below, I say, each 45-degree line, and then there's a little asterisk or dagger that says the lines drawn for q greater than equal to 0 here, minus q is the same as plus q. Okay, so let's get this up on the screen together with the, and I'm wondering, why is that computer so slow
See
today?
if there's any apps you can kill.
I bet you there are.
I don't believe I
apps
left
you could kill.
too much up. FileZilla you can click for sure.
Let me just take a look and see what is running here. That's
I guess I got it on the way out. Kill your mail.
that's a good idea. I wish I could kill that forever. Goodbye. Quit.
A good scroll.
And I don't need that guy either. So let's quit that. And let's quit that. Maybe it'll speed up now.
Google's a hog.
Oh, Google's a hog, you're right. Okay, I'm going to quit that. Okay, now we'll come back to that
That was
and
quick.
see if that goes. Now I can probably go ahead
Mm-hmm.
and get stuff pretty quickly here. There we go.
Get the culprit.
All right, we'll be back in business shortly here. And there we are. Okay, so just to make sure that we now know where those numbers go, and here's the matrix of those little coefficients. Okay, so every one of the numbers in any of those tensors has a little parentheses with a 1, 1, a 1, 2, a 1, 3, but the upstairs number is the rank 2, and we only are going to work with this one for the repulsion operator. We'll do some stuff with the first rank, that's the vector, this is the quadrupole. We'll do some work with that one too, just to show the method. And we'll use the matrix that we created at the very beginning of the class. Okay. Now, here's the formula, which I've checked very carefully, and I noticed that there's a -1 to the k missing from last years. That wouldn't affect us today because k is equal to 2 for the repulsion, but it will give us a minus sign when we go to the angular momentum 1 matrices that have rank 1, k equal 1. But in any case, this formula is golden. But this one with Eclipse Gordon has got an extra -1 to the k, which I tried valiantly to get rid of, but I can't, so it's there to stay. This formula is correct. It's just that I didn't have it there before. So we're relating the tensor KQ to the elementary by these arrays. That's what these arrays do. And we're interested in both, well, this one's really easy where the m's are equal at the bottom. That's the diagonal part of this thing. Those are the 0 tensors, the rank 2, 1, and 0, but then the components of the rank 0, that's scalar, 0, that's also scalar. These things all commute with each other. They're diagonal, all right? So that's the first part, but then these are the ones that actually make off-diagonal matrix components in the giant matrix that we were looking at, the 8x8 matrix that describes the doublets. Okay. So here's this, only 3 numbers here, and we usually don't even record that as a unit matrix in every situation. But then rank 1, rank 2, and then 3 and 4 and 5 as you go to bigger atomic shells. All right, so that's sort of it in a nutshell. We got a couple of more things I want to say before we actually do something here. This is the whole story over again up here. This is kind of a Dirac-like notational derivation of what I just put there. You can just say, I have a tensor operator here. I have a unit projector ket bra. And I've got another ket bra summed over M. This one's over M prime. Let's go to work. So there's the coefficient. There's the ket bra. Let's call the ket bra, and this will be true up to a constant, okay, the E M dot, or M prime M, okay, M prime M. That's what the elementary operator is. So, well, up to a factor. Now this thing right here is some combination, I've just put the mu here in, of Clebsch-Gordan coefficients that we just showed. Okay, so this is the thing that actually makes the coefficients, but there's an extra factor left out, that are parameterized by these parentheses, rank over two M numbers, Z component numbers. Index numbers for us, 1, 2, and 3 for our P shell. Okay, so this mu has this proportionality constant that we saw in the previous thing. That won't vary with those numbers, so you can use it. It's just be careful when you change rank. It does vary with rank, and if you're going another shell, of course it's going to change because the L will change then. Okay, so this is just another way to look at it. It may be useful to do that. This is another way to write out. It's not the one that we're going to use, but if you really get stuck, it's worthwhile just seeing how in elementary operators each one of these tensors is written. Just write them out, okay? What we're doing is we're taking V2, 0, okay? That's this guy here. He's 1 times E1, 1. He's minus 2 times E2, 2. He's 1 times E3, 3. Oh, don't forget the 1 over the square root of 6. But we're going to be multiplying 2 of these together, so I'm going to have 2 1 over the square roots of 6. That's 1/6 right there. So it's 1/6 of this collection of products of E's. Okay? That takes care of this tensor. Okay? And that tensor is a good part of the problem we're going to have to solve. But you may also need either one of these. We in fact need both of those. We need it in this order and that order. So we do them respectively, and they're very different. So this will be part of the E interaction, Coulomb, repulsion, Hamiltonian. And don't forget the very last of these, the two guys, -2 and +2. Put those together, 3 1 and 1 3, or 1 3 and 3 1. Those are the top rank and top Z component of the rank. Okay, so this is just another way to approach this that is really foolproof. This one is far, but it's a lot more laborious. You pay for your foolproofedness by working harder sometimes. Okay, so we're going to do the tableau basis. I wanted to go ahead and look at the dipole first, just for the heck of it. So I'm going to be looking at this guy, okay? But here's our great matrix that we worked so hard on getting all of these numbers. We didn't get these numbers up. Did we forget something? You can see what we have to do, right? I got to take this number and put it down here and change it from 1 2 to 2 1. I got to take this number and put it down here, 2 3 to 3 2, and so forth. Okay, so this is just the transpose of all the stuff that's on this side. So that's the whole thing right there. We had half of the thing before. Okay, and so now it's our turn to say put 1 2. If we're doing rank 1, we'd be putting the number in the 1 2 slot. For rank 1, if you pick that number right there, the -1 over the square root of 2. Okay, it goes with that normalization. Okay, so that's what we are about to do here. Okay, so I'm going to just look at rank 1. Okay, just to look at these numbers, But everywhere I see a parentheses with a 1, 3 on it, I'm going to be looking for a 1, 3 over here, and I'm not going to find it. Okay? So that guy's going to be out to lunch, but some of these, the 2, 3, for example, it is here. Okay? And it happens to be minus, and so forth. So that's what I would do to complete this. And there's the angular momentum operator LZ with its little square root of 2 times V10 that we talked about before. This one has a square root of 2 times the V11. And then there's 1 minus 1 is the lowering, I think. And it's probably a good time to catch up on this screen with that, just to keep all of these numbers visible and not all falling off of the corner like that. Okay, so let's go ahead and see what happens. First one I'm interested in is V11 diagonal. Okay. Ooh, what do we got here? V11, first of all, it's going to be asking for 2 times a 1, 1, and then 1 times a 2, 2. Okay. Now this is for the matrix element 1, 1, and 2. Okay, but this is a square. So what I have to do is take this matrix and square it, and that means I have to go ahead and do a multiplication of all these guys with these guys. So that's what's happening right here. So I'm going to be picking off a 1 times the 2, 1, and there's a 2, 1 right there. A 2, 3 squared, okay, this guy right there. And I'm being not careful with signs because it is squared. And then finally a 2 for a 1, 3. Now the 1, 3, we've got that, if we're going to do 1, 1, 2, let's see if I've got, yeah. I've got to go ahead and take the product there of that to finish this. This is V11. Let's see if I'm thinking correctly here. That is basically, yeah. So I'm going to be squaring that guy. I'm going to square that guy and add them. It gives me 2 of these. I think that's right. And 2, 3 squared, just 1, and I'm a little confused at this point. Let's see if I've got, I'm looking at the wrong number. I should be looking at the numbers from this table right here. Okay. So what I have to do is multiply each here, and if I'm squaring, I've got to square the result. I've got to take each one of these numbers here, mostly ones over the square root of 2. So that's where these come from, the 1, 3 position of this matrix here. And let's see if that's what I'm a little puzzled. I may have pulled this thing off of the, I think I sort of did this one last because it, and it may be that I took it off of the B11, 1, 2. It's 2. Those numbers look right. I am a little bit, and this is an off-diagonal one, which is crossing a 1, 2 with 1, 1, 3, the next door neighbor here. So this is basically multiplying this guy by that guy. And there's a lot of zeros in that one. That one comes out with a -1. Anyway, the upshot of this is that I'm going to produce this little matrix here, a matrix involving the diagonal 1, 1, 2, and then I'm going to have a coupling between these 2 guys right here. That's this matrix right here. So this is the beginning of the L dot L, that's L squared operator. And that gives eigenvalues if you diagonalize this little guy here of 3, 1, and 3. And that corresponds to having an angular momentum of J equal 2. Go ahead on this screen so that we can see that very far right hand side number there. put it on my hand there. There's a j equal 2 there, right there. There's a j equal 1 right there on my hand. And then there's another j equal 2 right there. So what those are is j times j plus 1, the eigenvalue for the square of angular momentum. J equal 2 times, that's 2 times 2 plus 1 is 6. So both of those belong to angular momentum 2, and this one belongs to angular momentum 1. So there's still something that bothers me about this particular one. I'll have to look at that later. But anyway, this was just a test to see if I get angular momentum. This is one of what we want, where we actually use the second rank tensor, this guy right here, and stick those numbers in from this table to wherever you see a 1, 2 there. Then you go look up the 1, 2 number right here and stick that in on top of this matrix right here. So that's what's being done here. Here's the first go through for that, just involving these two states, and then a pair of these two right here for the square, okay, and adding those up gives me a 4 instead of a 3. This one also gives it a 4, and then there's an off diagonal one, 1, 2, 2 to 1, 1, 3. That's the matrix that goes between 1, 1, 3 and 1, 2, 2. So basically we calculate this number, and then we calculate here, here, and here for V2 quadrupole squared. So there's the electrostatic interaction off diagonal element, and there's its diagonal element. So we get a matrix here analogous to the one for angular momentum, but this is for quadrupole, not dipole. That's a dipole like operator that's being worked on there. Now this one has, I'll leave that one and push this one forward. This is Q dot Q, quadrupole, quadrupole is what you would call it, but that's just all that the Coulomb interaction can provide for us. And these are the actual states that you can work out for using this matrix. We touched on this very briefly. The doublet D with m equal 2, and then the two doublet D and P with angular momentum m equal to 1. Of course, this one doesn't have an m equal 2, so there isn't anything up there, but there is something very much there. So we have a symmetric and anti-symmetric combination of those two tableaus that make up this Hamiltonian. So when I plug this vector in against this matrix, I'm going to be getting eigenvectors. Those are the actual energies in the units that were, totally contrived. Of course, we haven't worked out the Slater integrals that make these things into decimal values for absolute values of energy, but that's the electrostatic energy, and we've solved the whole problem for this particular multiplet. We're done now. The rest of them are just degenerates. You can go ahead and check to see if you get the same 3 and 5 for the energies of the, this one right here is J equal 2, okay? J equal 2 is lower than J equal 1. That's the P right there. That's this guy with a higher energy than this guy, who's going to have, according to this, a little over half the energy, okay? So we go ahead and just plot that prediction. That's prediction. Now, the thing we haven't talked about is the quartet. That's the other part of this P3 shell. It gives 0 for every one of the tensors that we've talked about. So we just put it as a baseline and then count up 3 for the doublet D and 5 units for the doublet P. All right? Okay. Well, you know what? When I first drew this thing, I didn't plot it that way. I said, hey, D, that's bigger than P, so put it higher. It's not. It's lower. By about that much. I mean, that's a prediction. Now, what I did was go and look on the Googly to see if I could find any nitrogen things. It looked like they had some young tableaus there, but those aren't young tableaus. They're just not anything. They're just boxes to put arrows in. Not anything. But there's a whole bunch of statements of Hund's rule, which is really what we're after here. And it's so fuzzy, you'll have to put on your glasses and look at your computer. But here's the only of these many Hund's rules. This is the only one that I think actually Hund would approve. Hund would poo-poo it. All the other Hund's rules here. This is the one that he actually said. He says, for a given electron configuration, the term with a maximum multiplicity, that means the quartet has a maximum multiplicity. The doublets, there are only two. This is 4, has the lowest energy. Okay? So that's where we are. I'm going to go ahead and move this guy up to the quadrupole region. And that's our prediction right there. With the, and I see that it's gone onto the chalk tray, but in any case, this says here that the multiplicity is equal to where the low spin angular momentum for all electrons. Well, I think that's something. Basically, the idea is a multiplicity is 2s plus 1, and s is the spin angular momentum of total for the electrons. So that's the Hund's rule number 1. Then, for a given multiplicity, let's say for the doublets, the term with the largest value of orbital angular momentum quantum number has the lowest energy. Okay? That's what we're getting. So this is right. The D is below the P, a little over half of the P energy. Okay? All right.
Did Hunt prove all these results himself, Dr. Harter? Did he just state these results, or did he prove them?
Sort of hand-wavingly.
Okay.
The hand-waving for the first one is that if you're most anti-symmetric, which we are with the this is something I haven't done much with, but here we are. This is the quartet, highest multiplicity, right? We're talking about that, which is an orbit that's completely anti-symmetric. So the probability for any of those electrons being in top of another electron, absolutely 0. And that means some sort of exponential function around that that possibility is 0 or close to it, right? So most of the electrons get to avoid the repulsion.
Dr. Harter,
Does that make sense?
you said completely anti-symmetric for the vertical one?
Absolutely.
Three particles.
Yeah, we're going to talk about that on the next lecture,
It
because
doesn't-
we still have to put spin in, and one of the ways we do that is we put the orbit and the spin together and then make one of those things up.
That's orbit.
That's just orbit.
Okay,
And
then
what
it makes
goes
sense
with it, what goes with it is a tableau just like it, but conjugate to
for
it.
spin.
Right,
That
horizontal.
would make it, if it is the conjugate of that, then it's still anti-symmetric, and then you will have a symmetric
The
combination.
orbit is anti-symmetric, totally.
Okay,
And
but
the
if you
spins
take-
are symmetric, totally.
So if you take the conjugate of a young tableau that is completely anti-symmetric, then it will be anti-symmetric still?
No.
It will be
Think
symmetric,
about
right?
this one.
Huh?
Here I take the conjugate tableau, right?
Uh-huh.
It looks just like that. And that gives you spin 1/2, a doublet. Okay? So the conjugate tableau, this is self-conjugate. Okay? So the tableau that goes with that, we're going to see is, spin up, and spin down. Has to be different in this slot right here. Always has to be down.
So if I want to build the wave function for the first one, for
This.
that one,
All of those guys need to have spin tableaus. There are only 2 of them for each that correspond to, one of them is up, up, down,
Mm-hmm.
and the other one is up, down, down. And that's it.
That's the conjugate of that.
And that's the conjugate tableau that goes with this orbit tableau. And this orbit tableau, you know, what 1, 2, and 3 mean, they mean orbital momentum, 1, 0, and -1.
But then that would be kind of like trivial in the up case, because they will always, you know, like fermions always have antisymmetric wave functions, right?
Totally.
Totally, yeah.
That means you take the electron with a spin, you don't separate it, right? You take the electron with some m and some spin m up or down, and you take that thing as a unit, and then you take the other two to go with the triplet, right? And
Yeah.
all of those together have to be in a wave function that's totally antisymmetric. And that's what you make by taking this guy here, who's totally antisymmetric, with a totally symmetric spin. You make an object, namely the total electronic wave function, spin and orbit, that is totally antisymmetric, and that's the Pauli rule, right? But you also do it with this one if you play the tableau game like we just described. Then again you get a wave function that is totally antisymmetric to interchange of the particles not leaving their spins behind or their orbit behind. They have to come as a package.
Now I ask you one question. I take the conjugate of that young tableau
This
down. No, down. The first one.
Oh, this guy.
Yeah.
Mhm.
That's still antisymmetric, right?
This is totally antisymmetric, no question.
conjugate-
The conjugate is totally symmetric. It has to be, because it's got to go with this guy and make something that is totally antisymmetric.
Then if I couple that antisymmetric for the state of that young tableau and the antisymmetric one, then I will have a symmetric, antisymmetric combination. That's
This state here,
only
the
one.
S quartet, it's S because that means angular momentum 0 obtained by antisymmetrizing this guy.
So I can still build up that state from that young tableau,
Yeah.
right?
Just think what's in that state. It's 1, which is angular momentum 1, right? 2, which is angular momentum 0, that's orbital angular momentum, okay? And -1 goes with the 3, right? So you're talking about 1, 0, and -1, that's 0. That's S. That's the orbital part, okay? And it's totally antisymmetric because it's been summed up with determinantal-like behavior that has an antisymmetry, okay? So that guy is completely antisymmetric, and he has all the antisymmetry that's needed when I put the spins that are symmetric with it. I can do 4 ways, not 4 ways, because it's a spin 3 halves. I go 3 halves, 1 half, minus a half, and minus 3 halves. That's 4, count them. And that's what this thing still has now. But this thing was only one thing, one orbital angular momentum 0 wave function that's got these 4 things hanging on it.
So the one on the right hand side, the labels S, P and D, they correspond to the added angular momentum, right? Like you add the angular momentum.
Mm-hmm.
Okay.
Yeah. The D, of course, is taking advantage of having 2 1s. Okay, if I take the right combination, and actually that right combination is written, I believe. Let's go and see if I can find that. Back a while here. See if I, yeah, there we go, right there. It may be a little hard to see, but let's take a look anyway. Here is the highest m value, highest z component angular momentum wave function of this spin doublet orbital D. That's orbital angular momentum 2. Okay, and you can see it's 1 plus 1 is 2, and then there's a 0. 2 stands for 0, right? So that's got an m component of 2, and then here are 2 states. One of them made out of the tableau 1, 1, 3, and another one made out of 1, 2, and 2. So this one's got an angular momentum of m equal to 1, and so does this one. That's the orbital part, okay? But then it's made out of this half symmetric, half antisymmetric tableau, just like this one is. And then here's the same thing made with a minus sign here, an anti-symmetric combination of those tableaus gives me something that's total angular momentum 1. This one has total angular, orbital angular momentum 2. And both of them, or all three of these states, have a single doublet, spin a half and minus a half, hanging on them. And that combination is partially symmetric and anti-symmetric. And the other one is partially symmetric and anti-symmetric. Or, in other words, what we have to learn to do is, with Klebs-Gordon coefficients, permutation curve, put those two together to make anti-symmetry. Total. It's a little more difficult than actually just multiplying right away. Here you got to multiply in sum to get the total anti-symmetry. But every one of these states has to be that. By that magic, we don't know why, Pauli exclusion principle, I guess is what, but it's Fermi-Dirac, is often the name we give to the statistics. It goes with fermions, right? Whereas Bose-Einstein is something that has integral spin, is totally symmetric. We play the same game with our spin and orbit to make that. There it's a little easier because you just get the symmetric guys out and put them together and you're done. For this one, just a little bit more has to be done in this particular department. But instead of having, like I did in my this figure that went in that paper, D should not be over P. That's a mistake, okay? And we've pretty well shown that. And the Hund's rule just says, in addition to let's go ahead and see if I can get Hund's rule up on here and read it. For a given multiplicity, the term with the largest value of the orbital angular momentum quantum number, have to add that, I guess, has the lowest energy. So here we are with that D of the doublets. The D has to be lower, has more orbit. And basically what that means, and this is the hand-waving argument, is that, and you need three hands because there's three particles here, but sorry, I can't accommodate you. You have to talk to the Martian down the hall. But the basic idea is they're going around together, they can easily go around together opposite, right? And if they're not going around together, they're going to run into each other more than if they are going around making higher angular momentum because they're together adding up to make the getting their angular momentum cones narrowed is really what it boils down to quantum mechanically, right? By doing that, they're having less electrostatic repulsion, so their electrostatic energy is lowered by almost a half than this one, where they're, well, I don't know how to do it. You know, I got to have one guy going this way and the other guy going the other way, right? Okay, you run into each other more when you do that. It seems. Hand-waving arguments only go so far, but that's pretty much all Hund had. This is a long time ago before you really did.
I think if I have to prove that Hund's argument, that thing, I think I will just use the probabilistic interpretation of the Klebs-Gordon coefficients and show that you have more probability of collisions of electrons.
That would be neat. That would, if you can pull it off. Let me show you what it is that we won't be, unfortunately, doing it. This is the rest of the tensor table here that puts D and P together, F and P, and F and D. Those are pretty much all that you get for the first 2/3 to 3/4 of the periodic chart. And so now, and this time I got it right, when you actually worked out the P3 as one of the configurations in these mixed configurations. I mean, you use the same sort of thing, except now your tableaus have large numbers in them because you got D here with 5 plus P with 3, so you've got 8 states. This is U8 with subgroups U5 and U3 determining all of the numbers for us. But the 2P comes up higher than the 2D very nicely there. And then the other ones have similar, just a few of them are shown. But here at the very bottom is angular momentum orbital 3 with a quartet. So this is pretty complicated atomic physics. Again, worked out by hand. This was not done by computer.
So was this from your 1976 Fuzrev A paper?
Yes, that's where it is. This is it right here, 76. Yeah. So yeah, the Tableau stuff works pretty nicely, even for something that complicated. But you see, the advantage here is I can do the calculate dipole transitions. There aren't any dipole transitions in the pure configuration, but here there are. You made one real thick here because the number was bigger, right? So these are things that let you do atomic physics. Atomic physics on a postcard. Well, it takes more than that. So we won't be getting into that. We've got other fish to fry. But it's worth you taking a look at it just to see if something suddenly happens where somebody discovers that they're putting a magnetic field on a configuration like that, you can calculate. So, somebody has crazy interaction for something, say a crystal field.
Still, nobody has a proof proof for spin statistics theorem in non-relativistic regime, right? It can only be proven if you
consider really proof there. It has no proof.
Oh, even in relativistic quantum?
You just make it an axiom.
But yeah, I can see how that
And it fits the data.
Yeah, I can see how that comes in when you solve the Dirac equation. You introduce that extra term in the Hamiltonian to make the commutator consistent, and then
yeah, you have to be working with something that respects fermions. You use fermion creation operators and all that. But that's the axiom, right? That's axiomatic. That's not a proof. It doesn't explain what really is going on.
This was formulated by Pauli, right?
Yes.
I don't know how he made such a profound guess. Like,
what's the only way you could build a periodic chart, right? Otherwise, all the stuff falls down to the ground state, right? This keeps it from falling down the ground state.
Dr. Harter, that paper is available on the website, right?
Not yet, is it?
It should be at some capacity.
This one? I have not scanned.
well, that you can even get it from the library.
Alternative basis, it's now on page 2 of the one I sent a link to you this morning.
That is good.
Okay.
Once
So-
again.
That's why, it's got
Oh,
those 3 that you
okay.
requested listed at the top.
Yeah.
Because I was looking for it. I think it's printer.
One second.
Doesn't
So
Let me,
13 and 1076. Okay.
You just follow that link that's in your email and everybody can follow that.
6. I think you can this one. Oh no, it's not 13.
It's
no, no.
been
Let's see
sent
if
out
I-
a couple times. It wasn't. Yeah, it's the one that says page 2 in it.
Okay.
I said you could, yeah, see, that's the enhanced page 2. It's got all the links.
this
and
guy
then-
right here.
This-
That's page 2.
Yeah, the one I asked you to paste over that.
This is page 3. And some of those links are useful, but they don't include.
Yeah, that's been overwritten too.
Okay.
And then I've got a follow-up page that's got all this supplementary stuff. I could have swear I've mentioned it a couple times, but if you follow the link on the email I sent back to you this morning, it'll take you right there.
Oh yeah, you can have it.
It'll even
Okay,
take you
I
to
did.
a keynote version of it, so you can
Okay.
paste it in.
Okay.
Maybe it got hung up on the
Yeah.
server. That's been known to happen.
Yeah. Yeah, this one's getting pretty crowded.
Yeah, it's all been reworked.
Okay.
So you just look at the new version. Don't even look at the
Yeah.
old version.
All right. Well, we'll make sure that this lecture 23 has that.
Okay.
Yeah.
Please do.
All right.
All right.